Hello viewers and welcome to another episode of Space Science with Python. In our today's video we are going to optimize the support vector machine algorithm we introduced last time. So we are not really improving our algorithm much, but I will show you a way how to fine-tune or how to search for better parameters in some machine learning problems. So in our case we will try to optimize the hyperparameters of the support vector machine. The world of search or parameter search or optimization and fine-tuning is really vast and huge, so I cannot cover all the things. I will only show the basic introduction into this topic. Scikit-Learn provides some very nice introductory material, like for example here a section about tuning hyperparameters of an estimator, where they for example use something called exhaustive grid search. So this is something we will use today, the function grid search, but there's a lot of other content shown here to give you an idea what kind of scores are there, what kind of metrics are there, and so on. But I would suggest not to be overwhelmed, because one does not have to know everything. It is always use case dependent and you cannot know all these things for sure. So be smart by knowing where you find the solutions. So this is here from the Scikit-Learn, and we will also talk a little bit about metrics, but also the world of metrics is huge. So also Scikit-Learn has a lot of different implemented scoring or metrics for machine learning algorithms like support vector machine, or also covering regression modeling, classification, clustering, and so on. So you see here for classification, clustering, and so on, the different metrics. Also here again, you don't have to know all these things. The basic concepts are quite important, like accuracy, or also what's the F1 score, the F2 score, what is the mean absolute error, the median absolute error, and so on. So this is like the basic fundament, and everything else will come over time. So you see also here this article about metrics and scoring is quite huge. I will provide both links into the description. Now, today we will continue working with the model we had last time. So I already prepared some small script, and also the first cells are probably familiar for you from last time. We import NumPy, Scikit-Learn, and so on. We have also here this grid search thingy I will explain later. In our second cell, we will also connect to our Google G Drive. So check if you have all the data that have been generated from the previous videos and previous Jupyter Notebook scripts, and also here the cells that load in the asteroid level 2 data. Here we are creating our class into our converting it into our binary problem, so converting it into X class and non-X classes. Here we are allocating the spectra in cell 5, and here finally, like in the 5th video of the machine learning project, we are making a stratified shuffle split, but only once for our case, to split the data into some training and some testing parts, and also creating a weighting for our support vector machine. Now the grid search algorithm is quite simple. So it's really just a dictionary you provide with a solution space, or not solution space, but with a space that should be covered by an algorithm, quite brute force, so to speak. In this dictionary, we will define what kind of parameters we would like to cover with our in our support vector machine search. So you basically call the support vector machine classifier, you train it, and then you train it several times with different parameters. And these parameters are defined by the dictionary we are defining now. And then the grid search is just taking the model, the classifier, and the dictionary, and you give it also some scoring, some cross-validation parameters, and then you do the fitting, and you just wait for a few minutes or hours, depending on your use case, for the final solution. Now this is also, of course, quite brute force, and this is also the very first section of Scikit-Learn, how to make this hyperparameter tuning. And we talked about this punishing parameters called C, that we would like to cover. So C is like, as I said last time, we don't have all, of course, data points that are perfectly separated. We have sometimes data points that are overlapping into the neighboring class. So a punishing parameter is adjusting this a little bit or taking this into account. So we are covering three orders of magnitude, namely 1, 10, and 100. And we do this for a certain kernel type. We do it for kernel, for the kernel linear, so for the linear kernel. Now you can also here put directly other kernels or put it into a separate dictionary. It doesn't matter. We can now put it here maybe in a separate dictionary. So you can also use the linear kernel, the RBF kernel we learned last time, the polynomial kernel, and so on. So there you can also cover different C parameters and so on, but I will show you later that there are also other searching algorithms that perform a little bit better than this simple brute force method. So this is our parameter space we will cover. So now we will create or instantiate our support vector machine class. So we take SVM SVC. Of course, do not forget the class weighting. Class weight. So the class 1 is the value we defined previously. So positive class weight. And then, of course, we need to scale also the data accordingly. So preprocessing dot standard scalar. And then we fit it on our training data. Train. Then, of course, we need to scale it. Very good. So this is now what we have here in this cell. And then in the next cell, we can now create our grid search. So let's call it like this. And we call this grid search CV, where we take the model. So the support vector machine we defined in the previous cell. We are providing the spaces, then the parameter grid. So the space of parameters that should be searched, and of course a scoring. And you may remember we talked about different scorings, about the F score. So there are like 3 F scores, and I would like to show you this picture here from last time about false negatives, true positives, and so on. Now we used an F1 scoring, which means it weights the precision and the recall similarly. So the precision has the same weighting as the recall. So the precision is simply the true positives divided by the true positives and the false positives. So the values that are wrongly classified as a negative, although they are true. And then, of course, the recall is the true positive divided by the true positives and the false negatives. So this is the space. Actually, it's the other way around. The false negatives are shown here in this green block here. So that's now the recall. And if we have an F1 scoring, both values have the same weighting. There is an F score called F0.5, which weights the precision a little bit more. And then there is the F2 score that weights the recall a little bit more. So yeah, it's a little bit up to you what kind of use case you have, whether you would like to create some kind of supportive tool or so. It really depends on what you want, what you try to achieve. But here in our case, we are balancing simply both precision and recall similarly, so you can later on play with other scores as well. Now let's write here the F1 score. And then also we create some kind of cross-validation 5. Now we can also now fit on the data. So we check the train X scaled and then the Y train. And now you will see the prompt. Well, it's spawning an error. I made a mistake here. It's now creating this 5 times cross-validation for the different values. So see here C1 and a linear kernel, C10 and a linear kernel, C100 and a linear kernel. And now it's iterating through all the parameter grid dictionary. And also you see the time it takes to compute it. And we finished. And you saw also the RBF kernel was quite fast. So here are now our different scores. And our final solution is now stored in the in our WCLF class that we defined here, the grid search CV. So what we can do now is we can assign a parameter final classifier where we say WCLF.best estimator. So this is how we assign the best estimator. So this is now our best solution. And of course we can print it out here. So we see the best solution is now C100 and the class weight. Okay, the class weight was as we defined it before. But let me check if we can also get params. We get also here more parameters. So here also with the kernel, the RBF kernel, it was not shown before. So here it is the RBF kernel and also some other parameters from our training. Okay, very cool. So we see also C100. It was also the last value from we defined here. So you could also try to test it out with the value 200 or 1000 or so. But yeah, this is kind of a brute force way, maybe a very good way for a very first approach to get a feeling and understanding of your classifier's performance. But later on, I would suggest to use more sophisticated solutions, but we'll get to this just in a moment. Now let's assign our test data. First, of course, we have to scale them as well. So transform the X-test data, and then we can create some predictions for the classes where we use the final clf.predict, and then we apply our scaled test data on this. So yeah, now we have our predictions. And with the predictions, we can, of course, compute our confusion matrix, as you may know it from last time. So let's import the confusion matrix. Import confusion matrix. Yeah, so now the confusion matrix equals to confusion matrix y test and y test prediction. So we compare our expectation with our prediction. And now we can simply print out the confusion matrix. And we could also now assign the true negatives, the false positives, the false negatives, and true positives also like this. So we say confidence matrix dot revel. Yeah, so you can play around with these values. And we see here, this is now quite a strong performance. We have in total 414 true negatives and 46 true positives. And yeah, here now we have the number 7 for the false positives, and for the false negatives we have 1 then, I think, just to verify that this was correct. Oh no, now I confused it. Correct order. So yeah, it was false negative. Yeah. So one of our spectra was wrongly classified as a false negative value. And now you can go back here again. You can also play around with other scorings. You can also put this here, also some kind of for loop if you would like to try out different scorings like F1 or precision or F0.5 and so on. So it's really up to you and depending what you would like to achieve. In our case, we could say, okay, we'd like to have an algorithm that that focuses, or that, yeah, it can provide a lot of, or not a lot, but it's more important to reduce this number. So we don't want to have false negative values. It's okay to have more false positive values because yeah, it's a tool that classifies the spectra, and the spectra are later reviewed by a scientist anyway. So it's more like a tool that, yeah, sorts out or reduces the huge amount of data, and later on a scientist will look on it anyway. So yeah, you would like to overweight the fact that false negatives are not welcome. So we can take a look here. So false negative is something we don't want to have. So false negative is here. So we do not want to over consider the recall much. Yeah, so the recall, or let's say we want to reduce this. We want to have this value as small as possible, but we do not care really about the precision. So we can have false positives. That's fine for us. So we could say, okay, let's overweight the recall a little bit. So overweighting the recall and weighting the precision is then the F2 scoring. So you could try to play around with the F2 scoring to get a better performance here. But you see, we do not have so many spectra to improve it significantly. Now it's only one spectrum. And I'm pretty sure when we run the script with a different number seeding that the numbers then here maybe 0 or 3. So we already have a very good performance, and it's not really necessary to over-engineer things here. Now, again, as last time, we can also now compute our recall score and precision score and the F1 score. Again, I already have this in my the clipboard. Oh no, I had it in the clipboard. I rewrote it. Doesn't matter. Let's do it manually. We say we take the recall score, we round the values by 3 digits, and we use Scikit-Learn.metrics.recall score y test and y test prediction. Yeah, there it is. And this is our recall score. We can then also create or compute our precision score. Let me copy paste it here. And then also our F1 scoring. So we use it also here with F1 score. And then we can simply print out the recall score, the precision score, and of course also the F1 score. And there we have our final results here with an F1 score of 92%. So quite successful for also this quite simple grid search optimization. I mean, compared to the last time, we already had very nice initial guess. So yeah, depending whether you would like to improve this more or not, it's already a quite feasible result for a scientific project. And of course, grid search is not the only one. So there are more methods, like for example, halving grid search, CVM, CV or so. So you can go here and for example, here there's this halving random search CV, a randomized search on hyperparameters. Also I think also there's one without randomizing, only the halving search CV. So there are a lot of different ways for this model selection, hyperparameter tuning. So you see it here, grid search CV, half grid search CV, and then randomized and halving random search CV. Try it out a little bit, play around. Mostly the grid search CV is always a very nice first approach, but it's, as it says here, quite exhaustive. And halving is like similarly, but it makes some, it uses specified parameters and makes a successive halving of the values. So it's approaching the best solution maybe a little bit better. Okay, so this is all for today's session. Again, the code is, as always, provided on the GitHub repository with some more additional information in some markdown cells and so on. And in our next video, we are going to create a classifier with not with support vector machine, but with Keras and with creating neural networks. So the next time, it's the very first time we will create neural networks. So I don't know whether you have already some kind of feeling or understanding of how neural networks work. I can highly recommend to to take a book or so and dive a little bit into the mathematics of neural networks. I will cover it a little bit next time, but if you are not really familiar with neural networks, it will be a little bit difficult to understand. So I would suggest to have at least some beginner's level of understanding how neural networks work. So we will not create some huge deep neural networks. This is not necessary for this case, but try to get a little bit familiar with it in the next week. And until then, I wish you happy coding and see you next time.